The global pandemic at the time of designing and the associated lockdown placed different demands on the living environment. More open private space became more important, houses with gardens were in demand, places open to their surroundings, bathed in sunlight, battling the confinement imposed on people due to health risks. Especially people living in a densely populated area felt the need for more open private space, it even went so far that the housing market saw an increase in the demand for open buildings and buildings with gardens. In response to this new reality came the idea of the playground house, a generatively designed structure with its own outdoor playground for each house. A playground which is defined as a place where a particular group of people choose to enjoy themselves, a place with an abundance of light but with the density of a Belgian city block, a place with different characteristics for every house, from private to open, from quickly accessible to enclosed, from high to low, and from large to small. This new typology, the so-called playground house, was designed on the old Rabot Tower site, a site in a densely populated part of the city of Ghent with about 9,700 inhabitants per square meter. The site is closely located to the city center and creates an environment that poses similar design problems as a normal city apartment: views into the city, connectivity between neighbors, how to deal with the surroundings, and so on. This project is designed on the basis of a symbiosis between computer and designer, a project in how generative design can create and inspire a designer to think differently. The symbiosis between the computer and the architect in this project can be divided in three parts of collaboration. First of all, the designer sets up a problem and the way to deal with it, which elements are optimized, how do you express them parametrically, and so on. The next step is closely connected to the first step and is a trial and error process. Based on the result of the computer, parameters, elements, IDs are changed. The third step is to make a feasible design of the proposal created by the computer and retesting it to maintain similar properties as the result in step 2. For the first two steps of the process, the design is based on a generative engine, creating hundreds of models and optimizing them based on different parameters set by the designer. This makes complex designs possible that take into account all those different parameters. Those parameters sets are mainly about views and sunlight and are done with Ladybug, a program that creates datasets from weather files and reflect those data onto the model. After the going back and forward between computer and designer, a design baseline was created in the form of a few elements with their corresponding optimizing factors. The first of these elements is a street network that was created based on a walk engine simulating the most likely roads to be walked on site. This as a baseline of a street network with a central square. Surrounding the square, amenities are placed, optimized to maximize their views towards newly created and previously existing streets. On top of the amenities, a wild landscape is made, allowing the disconnection between the busy N430 and the opposing buildings and square. Highs and lows determine the disconnection but allow for the amenities to be still seen from the surrounding roads. An infinite number of housing blocks of 140 square meters on average are formed and given a place in the playground house. They are optimized much like a plant has found its ideal shape over billions of years. Plants grow on the principle of phototropism. They optimize their shapes by chemically reacting to light and changing shape to optimize. Different plants have different strategies, from sunflowers moving their flower perpendicular to the sun to the common bean spreading its leaves parallel to the sun. When we delve deeper into the workings of leaves and their position to the sun, we can see how leaves adapt their shape and orientation to the benefit of the rest of the canopy. The upper leaves are more horizontal and elongated, allowing to capture the high sun and allowing for sun radiance to enter the canopy, benefiting the inner leaves. The lower leaves are more vertical and rounded, allowing them to capture the morning sun. They are more adapted to low light and function better on radiance than on direct sunlight. The elements of the playground house can be seen as a structure of individual leaves, each of which can change and move so that they can be optimized in terms of sunlight and sun radiance. The buildings are shaped to maximize the low sun but minimize the high sun. This allows the building to keep cool in summer and warm in winter and functions just like a tree. The program develops a structure so that each placement and shape of a house benefits the entire structure. Open spaces are created to allow sunlight to flow into the central square, and buildings are placed so that they have a minimum impact on the sunlight entering other buildings. This also takes into account the optimal maximum density, just as a tree maximizes the number of leaves to take full advantage of the sun. In addition, the buildings are also optimized to be open to their surroundings. This means not only an abundance of sunlight, but also views towards their surroundings. The program maximizes the percentage that every square meter of surface can see without being obstructed by the neighbor. The next element are open squares placed alongside those staircases. These squares can function as community gardens, open spaces, sport grounds, markets, and so on. They act as a mediator between the inhabitants and the passerby. Those squares are optimized in the same way as the housing element in terms of sunlight, with the one difference that the sun is always maximized. The squares are also optimized in terms of views towards the city, elevated squares that function as a lookout that allow for views over the city and into the playground house, with a maximum view of different points of interest in the city, like the cathedral, the Boekentoren, the brick chimney close to Dampoort, and so on. The second step of the process is to run and evaluate and rerun the program. With generative design, the result can be unexpected, both in a good and a bad sense. A lucky mistake can change your design for the better, a flaw in the system can create something useful for the designer, the unexpected of the computer or the lack of knowledge of the user can create something that otherwise would not have been done or been seen by the designer himself. On the other hand, the first iteration can result in dissatisfactory results, lack of density, or intersecting houses. Each iteration brings up a new problem. The way to solve this is by changing the design problem or optimizing patterns in the same way that the generative engine finds the best result. The designer has to go through a process of trial and error, learn from its mistakes, and develop the design problem further, until a satisfactory result is achieved. The final step is a design from the computer model to a building. The parametric model does not have the same complexity as the definitive building. This would require too much computer power and would prolong the process almost indefinitely. This also means that further steps need to be made in the design in order to not nullify the results of the optimized parameters. This re-evaluation is done by comparing the values of the parameter between the computer's end result and the designer's end result. The main flaws of the computer program are further designed and interpreted. For example, the elevated streets are now connected, creating loops going around the whole structure, creating walkways with a view from inside the playground house and over the city. Openings are made in the garden walls that act as structural elements that carry every individual housing unit and act in a similar manner as the walls of abbeys, creating a microclimate. The openings allow for views towards the surroundings and the city, but are placed in a way they still maintain privacy. Housing units are not designed and can be seen as a virgin site, allowing personal choices and design of the space, like a normal vacant lot. However, the size and dimension are already in place and need to be adhered to in order not to invalidate the simulation's result. This gives the feeling of ownership of your own piece of land, free to do what you want with a given building code. To battle dark and enclosed spaces on the ground level, a man-made impenetrable piece of nature is added onto the landscape. Open space is elevated, allowing for closed biotope space on the ground level. The final result is still a few steps away from an actual buildable building. Structure and circulation can be better implemented in the program itself, and logical questions about cost, efficiency, and materialization arise. Furthermore, the way in which a typology is constructed can be used for further developments. Because of less ground-bound typology, it can become a sprawl over the city, and it can grow over the urban fabric, densifying neighborhoods without losing open space. These bigger structures, developed on the basis of density alone, would require different parameters and new research in how to deal with designing issues apparent to that design, from light studies to how people interact with the space, from the elevated street network to the open space on the ground created. The idea of the project can form a baseline for a debate on how to live in a densely populated environment, yet feel like owning your own piece of land. It can give a vision of a new form of an open building, a building typology mostly desired by people in Flanders, and even more so since the pandemic.